Okay, so this is a electromagnetic induction question. So figure 1.1 shows a cylindrical aluminum bar resting on two horizontal aluminum rails placed 5 cm apart on a horizontal surface. So if you see from a side view here, okay, if you see from a side view, you'll see as a horizontal bar, okay? So the rail will be here. Okay. So what happens here is that, okay, the first two parts are 3 marks. Indicate the direction of current flowing through A. So basically the battery, a plus and a minus, will tell you that the current will go here and then flow downwards. Okay, so just downwards. And state the direction which A moves. So basically you just need to use Fleming-Stefan rule. Okay, force, magnetic field in your index finger, and current. You'll get your force which is towards the right. Okay, towards the right. The force will be towards here. So basically just rightwards. Okay. So next, in order to keep A stationary, the aluminum rails need to be tilted. Draw a labeled diagram showing the forces acting on A when the rails are tilted. Now, the magnetic field is in the paper, and okay, just this rail tilted. Okay, this um is because this force is perpendicular to the magnetic field. So when you look at it from this direction, right? Let's say for this side. So when it's still horizontal, how will happen is that there will be the free body diagram will be like this. There will be a magnetic force here while there is a weight downwards. Okay. So there is also a, let me just draw the magnetic field inside. Okay, the magnetic fields are all coming downwards into paper. Okay, that is how the B field is like. So for this to remain stationary, we need a force that is somewhere in this direction. Let me just highlight the direction. We need it to be somewhere in this direction. Okay, because the resultant is here. So we need in the yellow direction so that it will remain constant. Okay, so basically to tilt it, you can either, let's see, you can tilt this way or you can tilt this way. Okay. Now, when you tilt either of the direction, there will be a normal contact force. Okay, there is a normal contact force here as well. Okay, I should add that in as well. There is a normal contact force that is here. But now when you tilt it, the normal contact force changes direction. So it will be like in this direction or in this direction. And if you see, we need a force in the yellow color direction to actually balance these two. Okay, that's by the normal contact force. You have to bend, and only this is possible. So for part C, it will be bent in this manner. Okay, so when it's tilted, okay, draw a free labeled diagram. So it will be, for part C, it will just be tilted this direction. Okay, and if we see from here, current is out of paper. Okay, so you're just supposed to draw the forces. So basically, your forces, there will be a horizontal magnetic force. There is a weight. Okay, and because it's labeled, we need to spell it in full. Weight of rod. Okay, then this part probably I will just use text. Okay, magnetic force on rod. And last one will be normal contact force. So the normal contact force will be in this direction. Okay, and then just label normal contact force. Okay, so so this is pretty simple. Okay, last part, part D. Calculate the angle to the horizontal to which the rail must be tilted to keep the bar stationary. If the mass is 5 gram, current is 4 ampere, and the direction of field remains unchanged. Okay, so based on this, the direction of field is still going to be downwards. Okay, downwards. That's the direction of the B field. Okay, so the angle that we want is this angle. And if we tilt it, if you recall from dynamics, that will be this theta, which at the same time, it will be this theta as well. Okay, so you can either draw, you can actually easily draw tip to tail, or you can just resolve vertical and horizontal. Okay, but in this case, I will prefer to draw tip to tail because it's 3 forces only, so it's pretty straightforward. So this for part D, so basically I will need my magnetic force here. Okay, we can just label this as FB, then label this as weight. So we know that the weight is downwards, and the normal contact force, okay, just label this as N, and this will be theta. Okay, because that is the angle to the vertical. Weight is vertical. So we can see that from here, it's pretty straightforward. Tangent theta is just equals to FB, the magnetic force, divided by the weight. Okay, now what is the magnetic force? Okay, in this case, because it's perpendicular to the current, right, basically it's just going to be BIL. Okay, it's the B given as check. Okay, it's given that is 0.1 Tesla, and this part here is going to be 5 cm or 0.05 meters. So when we use BIL, we know the values here, and it will divide by mg. Okay, I'll just bring your attention to here. So tangent theta is equals to 0.10, the B, the current, which is 4.0, and the length, which is 0.05, divided by 5 grams, which is 5 over 1000, times 9.81. Okay, so here we can just press our calculator. Okay, let me just press the calculator. 0.1, okay, 0.1 times 4 times 0.05 divided by 5 grams divided by 9.81 multiplied by 1000. Okay, make sure your calculator is in degree modes. Okay, especially this is depending on what they ask for. Okay, sometimes they might ask for radians, sometimes they might ask for degrees, so you must take note. So you should get 22.2 degrees, and that will be the answer for part D. Okay.